Assalamualaikum warahmatullahi wabarakatuh, and a very good day to all. Welcome to Foundation Physics 1 PHY094. Today I'll be teaching basic quantities and units. These are the subtopics for this lesson: base and derived physical quantities and their units in SI, dimensional analysis, unit conversion, significant figures, and order of magnitude. You may refer to the learning outcomes here. These are the list of the base quantities and derived quantities that you're going to learn in this semester. For this lesson, we are going to focus to only three quantities: the length, the mass, and the time. For the length, the SI unit is meter. For the mass, the SI unit is kilogram. For the time, the SI unit is second. Again, these are the SI unit of length, mass, and time. For the length, the SI unit of length, the meter is defined as the distance traveled by light in vacuum during a time interval of 1/299,792,458 seconds. For the mass, the SI unit of mass, the kilogram, is defined as the mass of a specific platinum iridium alloy cylinder kept at the International Bureau of Weight and Measures at Sèvres, France. And for the time, the SI unit of time, the second, is defined as 9192631,700 times the period of oscillation of radiation from the cesium atom. Now we move to the next topic, dimensional analysis. Any valid formula in physics must be dimensionally consistent. That is, each term in the equation must have the same dimension. It means that the dimension on the left-hand side of the equation must be similar to the dimension of the right-hand side of the equation. To check the dimensional consistency of an equation, it is convenient to introduce a special notation for the dimension of a quantity. For this purpose, we will use square bracket. This is the square bracket to specify the dimension. Example, to indicate the dimension: for the length, the x must be in the square bracket equals to the dimension of the length, the capital L. For the mass in the square bracket equals to the dimension of the mass, the capital M. For the time in the square bracket equals to the dimension of the time, the capital T. For the derived quantity, for example, the velocity, V must be in the square bracket equals to the dimensions of the velocity, which are the length and the time. Let's use this notation to check the dimensional consistency of a simple equation. Consider the following formula: x equals to s naught plus vt. In this equation, x and s naught represent distances, v is a velocity, and t is time. Writing out the dimensions of each term, we have x in square bracket equals to s naught in square bracket plus v in square bracket, t in square bracket. It becomes the dimension of each quantity. The length equals to length plus length over time times time. Now, you can cancel the time, so it will leave only the dimension of length on the left hand side of the equation and length also in the right hand side of the equation. Okay, again, as a result, we see that each term in this formula has the same dimensions. This type of calculation with dimensions is referred to as dimensional analysis. Okay, let's see one example. Show that the expression x equals to s naught plus v naught t plus half at squared is dimensionally correct. Okay, please watch this video.
Now we have an equation: x equals to s naught plus v naught t plus half at squared. Now you want to check the equation is dimensionally consistent or not. So you want to check one by one. The dimension of x is written as x square bracket, it means that the dimension of x is written like this. Equals to this dimension, which is L, and then we note velocity. The dimension of velocity is written like this. We note in square bracket equals to length over time. It has two dimensions, so the length and the time, and then half has no dimension. Okay, and then the dimension of acceleration, or a in square bracket, equals to L over t squared. It means that acceleration has length dimension and time dimension, and then the dimension of time, t, equals to t. Or if you want to add t squared here, you may also add t squared for the dimension. Okay, now you will check the dimension. For x equals to, the dimension of x is length, x0 also the length, and then we know, equal to this dimension, L over t. Okay, remember the t. Okay, again, dimension of t equals to t. Okay, put t here, and then plus half. Remember x is the dimension, and then acceleration L over t squared, and then t squared equals to t capital squared. Okay, now you may cancel the dimension for the time and then for the time squared. So only the dimension of length remains in both sides of the equation. It means that the equation is dimensionally consistent. Thank you.
Okay, now we proceed to the next topic, unit conversions. It is necessary to convert units from one system to another. These are the example of the conversion factor. One of them is 1 mile equals to 1,609 meters and also equals to 1.609 kilometer. Let's say if you want to convert inch to centimeter, 15 inch equals to 15 inch times the converting factor between the inch and the cm. 1 inch equals to 2.54 cm by referring to this conversion factor. And then as you can see here, this inch can cancel with this inch and only cm remains in the equation. So that's how you convert the unit. Units can be treated as algebraic quantities that can cancel each other. Okay, let's watch another example. A car accelerates at 14 meter per second square. Determine the acceleration in kilometer per hour square. Okay, let's watch the video together.
Now we have 14 meters per second square. You want to convert this value to how many kilometers per hour square? So how? Have 14 meters per second square. Now you want to convert meter to kilometer. You need to know the converting factor between meter and kilometer. You know that 1,000 meters equals to 1 kilometer. You need to use this value to convert the unit. Okay, so you need to cancel the meter, so that you need to put 1,000 meter as the denominator, and then you need to put 1 kilometer as the numerator. So here we can cancel the meter. Next, you want to remove the second square, and then you want to insert hour square. Again, the same procedure, you need to know the converting factor. You know that 3600 seconds equals to 1 hour. But now, this is the converting factor between second and hour, not second square to hour square. You may want to add the square later. Alright. So, now, we want to remove the second square. So, you need to put the 3600 seconds as the numerator and then 1 hour as the denominator. Now, we want to insert the square inside the bracket half. You need to put the square outside the bracket first. Now, if you put the square outside the bracket, it means that you square all the value inside the bracket. It means that 3600 square, second also square, hour square, 1 also square. Now, you can remove the square outside the bracket. Okay, so the result will be, remember, you need to cancel the square. Now you have cancelled the second square. Alright, so remember 14 times 1 kilometer, or just bring kilometer divided by 1000. Okay, multiply with 3600 square divided by hour square. Okay, just ignore 1 square because 1 square is 1. Okay, so now you can calculate the value, and then the unit will be kilometer per hour square. Okay, thank you.
Okay, let's proceed to the next topic, the significant figures. The rules for identifying significant digits when writing or interpreting numbers are as follows. The first one, all non-zero digits are considered significant. For example, 91 has 2 significant digits, 9 and 1, while 123.45 has 5 significant digits, 1, 2, 3, 4, and 5. And next, zeros appearing anywhere between 2 non-zero digits are significant. Example, 101.12 has 5 significant digits, 1, 0, 1, 1, and 2. Leading zeros are not significant. For example, 0.00052 has 2 significant digits, which are 2 and 5. The trailing zeros in a number containing decimal points are significant. For example, 12.2300 has 6 significant digits, 1, 2, 2, 3, 0, and 0. The number 0.000122300 still has only 6 significant digits. The zeros before the 1 are not significant. This convention clarifies the precision of such numbers. For example, if a result accurate to 4 decimal places is given as 12.23, then it might be understood that only 2 decimal places of accuracy are available. Stating the result as 12.2300 makes clear that it is accurate to 4 decimal places. The significance of trailing zeros in a number not containing a decimal point can be ambiguous. For example, it may not always be clear if a number like 1300 is accurate to the nearest unit and just happens coincidentally to be an exact multiple of 100, or if it is only shown to the nearest 100 due to the rounding or uncertainty. Leading or trailing zeros can make it hard to determine number of significant figures. For example, 2500 or 0.000036. Each of these has 2 significant figures. This one has 2 significant figures. This number also has 2 significant figures. Scientific notation writes this as a number from 1 to 10 multiplied by a power of 10, making the number of significant figures much clearer. For example, 2500 becomes 2.5 10 to the power of 3. So it means that this number has two significant figures, 2 and 5. If we write 2.50 times 10 to the power of 3, it has three significant figures, 2, 5 and 0. You may also write this number in terms of scientific notation, 0.00036 to 3.6 times 10 to the power of negative 5. So it has two significant figures, 3 and 6. So number of significant figures after multiplication or division is the number of significant figures in the least known quantity. And when physical quantities are added or subtracted, the number of decimal places after addition or subtraction is equal to the smallest number of decimal places in any of the individual terms. The last topic for this lesson, order of magnitude. For many problems, knowing the approximate value of a quantity within a factor of 10 or so is sufficient. This approximate value is called an order of magnitude estimate and requires finding the power of 10 that is closest to the actual value of the quantity. For example, 75 kilogram is approximate to 10 to the power of 2 kilogram, where the symbol, this symbol means is on the order of or is approximately. Increasing a quantity by 3 orders of magnitude means that its value increases by a factor of 10 to the power of 3 or 1000. This is the last example for this lesson. How many $1 bills stacked one on top of the other will reach the moon, so that you can build a bridge between the earth and the moon using money, using dollar bills. Now we estimate that 10 stacked bills form a layer of 1 millimeter, and then we convert millimeter to kilometer, and then we multiply this value by the approximate lunar distance, which is 4 times 10 to the power of 5 kilometer, multiply with the number of bits per kilometer, which is 10 to the power of 7 over 1 kilometer. So you need to have 4 times 10 to the power of 12 bits in order to build the bridge using the dollar bills from the earth to the moon. Okay, that's new knowledge for us. Thank you for your time. See you again in the future.